So thanks for the kind invitation to speak at this symposium. So I was going to talk a little bit about our research, a little bit about the department, and the background. So yes, I studied in Canada. I'm part Canadian, and then I did my postdoctoral work in London at the Ludwig Institute for Cancer Research. And my first independent post was at the Babraham Institute, which is just south of Cambridge. It's about 10 kilometers south of Cambridge, where I established my first group between 2003 and 2017. And then in 2017, I came into Cambridge, just down the road here on the Henry Court Road, where I took over Dr. Klause's post as head of the Division of Immunology. So I was asked just to summarize a little bit about the Department of Pathology. It's an old department established in 1893, and the current head of the department is Professor Jeff Smith, who's a virologist who works on vaccinia virus. And the department has about 40 research groups divided into 4 divisions. So I'm chairing the immunology division, the virology division, one dedicated to microbiology and parasitology, and one dedicated to molecular cellular pathology, most of which is related to cancer, to understanding diagnosis and so on for cancer. So all the department, this is an advantage and disadvantage at the same time sometimes. So we are divided by the central Cambridge area on Tennis Court Road, but then about half the department is under Admiral's Hospital as well. So that offers some logistical challenges in getting us all together and discussing, but it also offers possibility of having collaborations on both sides. And perhaps in terms of the impact from the department, the most important was the development of CAMPath. So this is an antibody drug developed by Herman Waldman and colleagues while he was in the department against a molecule called CD52. So this drug was initially developed for the treatment of leukemia, that's a disease I'll come back to, kind of a blood cancer, and more recently it's been approved for the treatment of multiple sclerosis. So in fact, the department has had an income stream from this drug over the years, and that's also benefited us and allowed us to fund Ph.D. studentships and sometimes bridge research between grants and these kind of things. So now I'm going to switch slightly to talk a little bit about science. So this is a very exciting time to be an immunologist. There is great progress, I think, in developing new vaccines against viruses, bacteria, and parasites. But the one thing that has really caught the world by storm recently is the ability to train the immune system to fight cancer. And this was celebrated last year when Jim Allison and Klaus Okkenhaug were jointly given the Nobel Prize for their work in training the immune system how to kill cancer cells. And it's actually based on a very, very simple principle that the two of them came up on separately. And that is T cells here, which are roaring to, in this case, kill a cancer cell, or here, being trained to kill a cancer cell by another cell type in the immune system called the dendritic cell. Now, what people realized quite early on was that as important as activating the immune system, you needed to have a mechanism to shut down the immune system at the end of it. And these are sort of what we call the brakes of the immune system. Two of those are either called CTLA4, which is expressed by T cells, or PD1. So both Jim Allison and Klaus Okkenhaug realized that these are important brakes for the immune system, and if we take those away, we can unleash an immune response. And the first thing everyone thought about when they learned about that is that this can trigger autoimmunity. And indeed it does. If you remove these molecules, you end up with an autoimmune reaction. But both of these also realize that we can take this to our advantage. So in diseases such as cancer, where the immune system is being suppressed, if we remove these brakes, CTLA4 or PD1, you can then have more persistent, or in fact, sometimes induce a much stronger immune response. And this works. So the first proof of concept for this was an antibody against CTLA4, which was a trial in melanoma patients. And although it wasn't highly effective in initial trials, what was remarkable was there was a small subset of patients, about 20% of the patients, who showed very, very long-term remission. So prior to this, once the melanoma went metastatic, once it spread to the rest of the body, it was an almost certain death sentence. It appeared that a certain percentage of patients who might die. The anti-PD1 antibodies worked even better, so sort of got to like sort of 30 or 40% in some studies, and now some people are trying to combine them. When you combine these antibodies, sometimes you get a more potent anti-tumor response, but then also the patient starts suffering from autoimmune diseases. So the challenge really now in the field is to try to come up with either dosing or permutations where you get a maximal anti-tumor response, but you don't have severe autoimmune. And the reason why we are so excited about this, now this has gone beyond melanoma. There are about a dozen cancer types that you can treat with immunotherapy. Some much better than others. Ironically, the more mutated the cancer is, the better it works. It's talking about the lung cancer, where you have mutation caused by cigarette smoke, or blood skin cancer, where the sun has caused a lot of mutations. Other tumors that don't have as many mutations, it doesn't work as well with the inhibition strategy. So, my career has been on this funny group of enzymes here called PI3 kinases. And I'm going to switch speed a little bit, I'll come back to this. So these are enzymes inside the cell that get activated by receptors that sit on the surface of the cell. These receptors can get phosphorylated, so this is the signal that then recruits these PI3 kinases to come up to the plasma membrane, to the near the outside of the cell. They get further activated there, and then you see this little molecule here, it has two phosphates. So when this enzyme here gets activated, you get a third phosphate on this particular molecule. And that makes all the difference. And I go to conferences with thousands of people where maybe a few hundred study these two phosphates, but most of us all are focused on this phosphate, called the 3-phosphate for PI3 kinase. So this was discovered about 30 years ago, and this works because you have certain proteins within the cell that can only recognize this molecule if it has all 3 phosphates, and in particular this one on the 3 side. So this is why we call it PI3 kinase, because it's a molecule that adds the 3rd phosphate in this group. It will recruit proteins to the membrane that either inhibit other molecules or activate other molecules. So that in a nutshell is something that I learned about when I started my Ph.D. 25 years ago, and I've worked on these enzymes ever since. And one reason I became fascinated by these enzymes is that whereas in simpler organisms you only have one of these, in humans we have 4 of these enzymes. So we call these PI3 kinase alpha, beta, gamma, delta, basically named in the order during which their genes were discovered. PI3 kinase alpha and PI3 kinase beta are expressed in most cells in your body, whereas PI3 kinase delta and PI3 kinase gamma have immune-specific functions. So these have been adapted to help our immune responses. PI3 kinase alpha is also one of the most frequently mutated genes in cancers. We know that this enzyme here is very, very important for the cancer, whereas these enzymes here are very, very rarely mutated in cancer. So that gives you one clue of why they're different. And we've done a lot of biochemistry and genetics and pharmacology to try to tease out all these other differences, to just answer the simple, basic scientific question of why we have these 4 enzymes, and then after the therapeutic opportunities, can we target each of these enzymes for different purposes to treat different diseases. And then both of these have been quite productive. So the most obvious one is targeting PI3 kinase alpha. So I mentioned that this enzyme is mutated. This is sort of a schematic of mutations. So you see loads and loads of mutations at 2 hotspots in this gene. And in some breast cancers, for instance, 40% of women will present with some mutations in this gene. So phenomenal Darwinian selection of these mutations during the evolution of a breast cancer. And only last month, a drug against this enzyme was approved. I'll just talk about that a little bit last year. It's called APDS, because it inhibits the alpha isoform of PI3 kinase. About 5 years ago, another inhibitor called deletion, which inhibits the delta isoform, was approved for chronic lymphocytic leukemia and subsequently for another blood cancer called indolent non-Hodgkin lymphoma. What's interesting is in this case, you will never find mutations of PI3 kinase in these cancers, but nevertheless, these cancers are exquisitely dependent on this isoform for their survival. And more what I want to discuss and try to convince you is that we also believe that this target here, PI3 kinase delta, can do some of the things that the drugs against CD4 and PD1 can do. They can unleash anti-cancer response. We can actually, paradoxically, use inhibitors of these kinases to activate and train the immune system to kill cancer. And that's completely opposite to what I started my career. I always thought these were going to be things that shut down immune systems, but they're actually shifting the immune response towards from one function to another. So this is what these kind of studies do. So you put cancer patients on trials for these drugs. Some cancer patients will be given a placebo, some will be given the real drug. Neither the doctor nor the patient will know what they're given. And then at the end of the study, you open the secret envelope and find out who was in what. And this is an interesting one. So you can see here that there is a separation here. So the patients who got hormone therapy, which is a standard therapy in breast cancer, and this PI3 kinase alpha inhibitor did better than the patients who only got the hormone therapy and the placebo effect. But this drug was only effective in patients who had this particular mutation in PI3 kinase alpha. The drug did not make any difference in patients who did not have this mutation. So this is a new area in medicine, many people call personalized medicine, where actually you have to diagnose at a genetic level the type of mutation within the cancer, and then you prescribe a drug accordingly. And there have not been very many approved so far, but this is approved here at the same time as this particular genetic test to find mutation was approved. So what you can see is in cancer, looks like good news. In my lab, we say that two curves are significantly different if you can shine a laser between them. And you can see I can just about do that. Whereas here, this is not significant because I can't shine this laser. But what's really important to remember, though, is that although this works, and it doubled the progression-free survival of these patients from about 5.5 months to 11 months, so potentially you can double survival, but none of them have been cured. All of these women will eventually succumb to the cancer. So that's the issue. So this is progress, but we're certainly not reached the goal yet. In the leukemia I talked about, it's a little bit different. So here the patients is actually quite radically better than the patients who were on the placebo control. In fact, they did so well that they had to stop the trial early, because although the doctors hadn't been told he was on which drug and the patients didn't know he was taking what drug, it became pretty obvious who was doing well and who wasn't. At that point, all the patients who were not doing well but were still surviving were offered a chance to get back onto that drug and in fact were helped by that. So that was a big success. This drug works a little bit differently than typical cancer drugs, in that if you just add this drug to the cancer cells themselves, you don't see a lot of cancer cells dying. Killing cancer cells is always the aim of cancer therapy. Instead, what this drug is, it interferes with lots of molecular mechanisms that keep these cells in the lymph node where these cells grow and grow and grow uncontrollably. So by disrupting a lot of these interactions, these transformed B cells, in this case, they go into the bloodstream where they are more susceptible to undergo apoptosis, often aided by other therapies given concurrently, whether those are chemotherapies or antibodies like Babraham. So it's a different mechanism that you wouldn't necessarily have discovered in the classical kind of screen against toxins that would kill cancer cells. Now, one problem with this drug is it comes again with some severe side effects that are not dissimilar to the patients who were treated with anti-CD4 and anti-PD1. So these patients will raise an inappropriate immune response against all the bacteria in your gut, and they often get colitis, diarrhea, and those kind of things. Some will get skin rashes because they have inappropriate immune reactions against bacteria over the skin, or they get pneumonia. There's also some failure to cross. So the drug is actually not terribly well tolerated, even though it's very, very effective. And there are other drugs now that are perhaps used in preference. But it's a very important proof of concept that you can target such a pathway so effectively. This adverse effect we now know is because this drug hits a very important T cell subset in your body called regulatory T cells. And it's quite a remarkable fact that if I took blood from any one of you and I got rid of all the red blood cells and looked at all the white blood cells, about 1% of all of those blood cells in your blood are this little guy here, the regulatory T cell. However, if somebody could eliminate that cell from your body, you would have about a month to live before your immune system overwhelmed you and you had a massive autoimmune reaction. You had massive spleens, massive lymph nodes, and unfortunately, some children are born without these cells, and unless they have had a bone marrow transplant or some other therapy, by the time they are 2, they will also die from that disease. So this is a very, very potent cell that plays an important role not only in protecting ourselves from our own immune system, but this cell is also co-opted by tumor cells to protect them. So when you open up a tumor, you often find there's lots and lots of these regulatory T cells in this tumor that either have been recruited to this tumor or have been expanded within the tumor so that the tumor can protect itself against the onslaught of the immune system. And what we found is that when you target this cell, that this cell is highly sensitive to inhibition by PI3 kinase delta, even more sensitive than the killer T cells that are actively trying to kill these tumor cells. There are other immune suppressive cells also in the body that act in a similar way that I don't have time to go into detail. So the big surprise for us, and this is now all at the level of mouse models, is that when we had PI3 kinase delta deficient mice that didn't have any PI3 kinase delta enzyme at all, we found that a substantial proportion of those survived when we injected them with tumors, whereas all of their wild-type litter mates could not survive these tumors. They only had about 3 weeks to live after we had given them cancer. And even more impressively, when we were able to use some fancy genetics to delete PI3 delta only in regulatory T cells, we really improved this survival benefit. So the challenge now is to come up with a therapeutic way to do this in humans, where we can preferentially inhibit these regulatory T cells and have this kind of anti-tumor response in humans. And this work is starting. It's looking quite promising so far, but we have a long way to go to understand exactly which cancer you may treat this in this way, how you're going to give this drug to minimize the side effects versus having a strong anti-tumor response, and also what kind of drugs it may be combined with. Do you combine this with other immunotherapeutic drugs? Is it best given shortly after surgery? These kind of questions. So these are big, important questions that you have to answer in this field, and have to answer and try to ask in an intelligent manner, rather than just starting lots and lots of clinical trials without having thought about the mechanism. So that's where we think we still have a role in this game, is to try to understand some of the cellular and molecular events that allow for this phenotype. So, but this has been taken forward. So a friend of mine, Christian Ottensmeyer in Southampton, is trying a PI3 kinase delta inhibitor in head and neck cancer. So this is a non-immunological cancer, which usually doesn't express PI3 kinase delta. But his idea is that by targeting regulatory T cell in this tumor, that may be an effect. And that he's just writing up the results from that first trial now, where he saw that had a number of these similar effects. So that's sponsored by Amgen and Cancer Research UK. And then there's another company in the States called Enzymes that also have a PI3 kinase delta inhibitor that they are now trying again several non-immune cancers. So our hope really is that this fascinating group of kinases that I became so enamored with when I started my Ph.D. can be used much more broadly, both to target tumors themselves by a number of different mechanisms. I mentioned one of them now in the breast cancers, and also by inhibiting certain immune suppressive cells in the tumor environment to unleash these kind of immune-mediated attacks of these tumors. So I'd like to finish there and highlight 2 people in my lab who really drove this work forward, with Dal Soon and then Lim, and now carried forward by Yogi now and now. This has been working alongside that lab. I have to say I don't do that very often, but somebody took a picture of me when I did, and other groups. And we also have had wonderful collaborations, both in Hamburg and before, in pharmacy, and funding for one countries, NRC, and 3 years or so. So with that, I'm happy to take a few questions if you have some.